Hi, hola, bonjour, and Salaam. Welcome to Blueprint Bazaar. In this second part of our plastic shredder machine full assembly walkthrough, we focus purely on the assembly process using SolidWorks. Unlike part 1, where the frame was created and components were positioned in their approximate locations, part 2 is all about bringing those pre-placed parts together into a properly constrained and fully functional subassembly. No modeling or part creation is done in this video. Our attention is entirely on assembling what has already been placed. We begin by revisiting the layout established in part 1, where the main shredder frame and various components, such as the side-mounting plates, were inserted into the assembly space. In this walkthrough, we systematically apply appropriate mates to join these parts accurately. Using SolidWorks assembly tools, we align the side plates to the frame with precise coincident and concentric mates, ensuring everything is fixed in its final, functional position. The goal is to transition from a loosely arranged collection of parts to a structurally sound and fully assembled section of the plastic shredder. Throughout the video, we highlight the importance of maintaining alignment, symmetry, and correct spatial relationships among the parts. This phase is essential because the proper positioning of the side plates directly affects how the internal components, like the shaft, bearings, and cutting blades, will fit and function later on. The mating process also ensures the frame is ready to receive loads during future operation or simulation. Viewers will see how to apply constraints methodically to maintain assembly integrity while keeping the design flexible for adjustments down the line. This video is ideal for those who want to understand the practical aspects of CAD assembly in SolidWorks. It demonstrates how to transition from a visual layout to a mechanically accurate and well-defined assembly without returning to part modeling. Whether you're a student, a SolidWorks beginner, or a professional refining your workflow, this session reinforces the critical role of precise part mating and alignment in building real-world mechanical systems. The plastic shredder machine is a mechanical device designed to reduce large plastic waste materials into smaller, manageable pieces. It plays a critical role in plastic recycling by enabling the breakdown of plastic items like bottles, containers, packaging, and industrial scrap into uniform flakes or shreds. These shredded pieces are easier to handle, store, and process in subsequent recycling operations, such as extrusion, pelletizing, or molding. The machine's robust structure and mechanical efficiency make it a valuable tool for waste management systems, recycling plants, and even small-scale workshops focused on sustainability and material reuse. At the core of the shredder is a set of rotating shafts mounted with interlocking blades or cutters. These cutters are designed to grip and tear through various types of plastics, rigid and soft, while maintaining the strength needed to handle high loads and continuous operation. The blades are typically made of hardened steel or other wear-resistant materials to withstand the mechanical stress of repeated shredding. These rotating elements are supported by bearings housed in the side plates, which are in turn mounted onto a rigid frame that absorbs vibration and ensures machine stability. The entire assembly must be precisely aligned to avoid operational issues like uneven shredding or mechanical failure. The shredder is powered by an electric motor, often connected to the shaft through a gearbox or pulley system that increases torque while controlling rotational speed. This controlled motion allows the blades to operate efficiently without jamming or overheating. The machine may also include a feeding hopper at the top, where plastic waste is introduced, and a discharge chute at the bottom to collect the shredded output. Some designs are equipped with safety sensors automatic shutoffs, and maintenance access panels to make the machine safer and easier to operate. All components are arranged in a modular format to simplify maintenance, part replacement, and upgrades. Structurally, the shredder must be engineered to resist the cumulative forces of operation over long periods. That's why the frame is typically constructed using square tube profiles and reinforced joints, assembled with precision in CAD software like SolidWorks before being fabricated. Mounting plates, motor brackets, and shaft holders are all critical sub-assemblies that ensure the machine operates as a single, cohesive unit. Each element, from the frame to the cutting assembly, is designed not only for strength but also for manufacturability, making the shredder practical for production and use in both industrial and small business contexts. One of the most critical aspects in the design of a plastic shredder machine is its ability to handle a wide variety of plastic materials, including HDPE, high-density polyethylene, LDPE, low-density polyethylene, PP, polypropylene, PET, polyethylene terephthalate, and PVC, polyvinyl chloride. Each of these materials has different mechanical properties. Some are soft and flexible, while others are rigid and brittle. The machine must be versatile enough to cut through these without excessive wear on the blades or generating too much heat that could deform the plastic or damage the internal components. Cooling and lubrication are often overlooked, but essential factors in larger-scale shredders. Continuous shredding generates friction, and in high-throughput operations, this can lead to significant heat buildup. Industrial shredders may be equipped with external cooling systems, or the blades might be designed with ventilation gaps to maintain lower temperatures during use. Lubrication points are also critical, especially for the bearings and shafts, as proper maintenance ensures smoother operation and extends the lifespan of mechanical parts. From a design perspective, CAD modeling tools like SolidWorks allow engineers to simulate the mechanical fit and motion of every part before fabrication. For example, interference detection can help ensure that blades won't collide or that the shaft rotates freely without obstruction. Engineers can also perform finite element analysis, FEA, on critical parts such as the shaft or the frame to check stress distribution under operational loads. These simulations reduce errors in physical manufacturing and ensure the machine meets safety and durability requirements. Another valuable feature in many modern shredders is customizability. Based on end-user requirements, the machine can be adjusted in terms of blade type, single shaft, dual shaft, or quad shaft, number of teeth, gap between blades, or the size of the mesh screen that determines the final shred size. Some designs also include reversible motors that allow the shredder to reverse the blade rotation in case of jamming, preventing downtime and mechanical damage. This adaptability makes the shredder suitable for both small-scale recycling setups and large industrial applications. Lastly, from a sustainability and environmental perspective, the plastic shredder machine is a key enabler in the circular economy. By reducing plastic waste to a reusable form, it minimizes landfill use and supports recycling processes that turn plastic back into usable raw material. When integrated into a larger recycling system, it helps close the loop in plastic usage, contributing to reduced environmental impact and more responsible resource consumption. With the side mounting plates now fully assembled and securely constrained to the frame, we've taken a significant step toward completing the plastic shredder machine. What began in Part 1 as a structural setup and visual placement of components has now evolved into a mechanically aligned and assembly-ready unit. Every mate applied in this walkthrough contributes to the machine's overall precision, ensuring a strong and reliable base that can support the mechanical operations ahead. This kind of accurate subassembly work is what transforms a rough concept into a practical, manufacturable design, and it's essential for anyone working in the field of CAD modeling, mechanical design, or engineering product development. As we continue building this machine step by step, each phase will add complexity and depth to the design. With the foundation complete, we're now ready to move forward with installing rotating shafts, shredding blades, spacers, and bearings, all of which rely on the correct positioning established in today's assembly. If you're following along with your own model, take this time to double-check your mates and ensure symmetry, alignment, and mechanical intent are preserved. At Blueprint Bazaar, we believe in showing not just what to do, but why it matters. Our aim is to provide detailed, real-world CAD projects that go beyond surface-level tutorials. Whether you're a student trying to improve your skills, an engineer working on real equipment, or someone passionate about mechanical design, our content is here to guide, inspire, and educate. Thank you for watching part 2 of this full assembly walkthrough. We hope it provided clarity and practical insight into how to bring your placed components together into a fully constrained structure. Stay connected with us here at Blueprint Bazaar as we continue this series, dive deeper into the internals of the shredder, and gradually transform this design into a complete, working machine. Until next time, keep designing with precision and purpose.